Okay. All right. So welcome, guys, to yet another session of uh, Databricks data engineering with Apache Spark. So we have been discussing the basics of the data frame, Apache Spark, how to process data, data ingestion, transformations, um, different processing techniques like from bronze to silver to gold, how we do transformations, data cleansing, how we do aggregations, right? And under the hood, how Spark is actually doing the processing. So we'll continue that today. We'll touch upon, we'll just review some of the concepts that we have done, and basically to reiterate the concepts of data frame, how Apache Spark is processing, the distributed processing. We'll touch upon how caching works, and then we'll review some of how to do the Spark SQL within the data frame, like what we are doing, the data frame operations using PySpark. We'll also see how we can do Spark SQL. So I'd like you guys to engage and participate in this and start practicing. I believe our friend Subbu has done some practice. He was reaching out to me yesterday for some issues, and while he was doing something related to the cluster and all that. So it's good that people are getting started with hands-on, starting doing some of the practice. So I encourage you all to just do the uh, basic data pipeline processing, right? So just take one data set, read, transform, and write, right? And then you can try out different transformations. That's the first part of it. It's basically the same kind of the ETL route, right? So you ingest data, you transform data, and then you load the process data. So then you can proceed with adding, doing the joins, um, doing Spark internals, how to efficiently process the data, right? And then we slowly move on to the other concepts of the Databricks, Lakehouse Delta. So how Delta does the Unity catalog, the features of Delta, like, the time travel or optimization using Z-order or vacuum, all of these features that Databricks Delta provides as part of the Lakehouse, within the Lakehouse, and Unity catalog, how you manage your different tables in the different layers of the Unity catalog. And yeah, so we'll continue whatever we have, the concepts of Databricks, and then we'll move on to the uh, move on to preparation for certifications, kind of a thing. Okay, so that's how we are going to structure this training moving forward. So basically today, yeah, as I said, we will touch upon reviewing some of the concepts and caching, and then we'll focus on uh, to understand how the data processing is being done. Is that clear? Anybody having any questions? Hey, Hari, welcome.
Yeah, hi, Arun.
Hi. We have Akshata. Hello, Akshata. Good morning.
Hi everyone, good morning.
Hi. So we have Subbu. Hey, Subbu. Good morning.
Hi, Harun. Very good morning.
Fine. So Subbu, you are doing some practice. What?
Yes, up to gold, I completed what we gave the last time task.
Okay.
So extract, load, and transform and load. bronze, silver, and gold.
Okay.
Those tasks completed.
Okay. Yeah, nice. Hi, Satish. Good morning.
Morning, good morning.
Nice. So anybody else have been doing the hands-on practice? Pawan, yes. Yeah, Pawan has already reached out to me. Yes. Okay. So yeah, I encourage everybody to get started. So we have shared some of the sample data sets and notebooks as well. Just download those data sets and start executing, writing your own transformations using the notebooks. Okay, that is what will give you a good hang of things, when you start doing hands-on. Okay, so let me get started with the where we left off. So we were talking about the Spark internals, right? So the stages, jobs, and stages, right? So anybody want to comment on what we have learned in just few lines, maybe about how the data processing is happening when you have a sequence of transformations and actions within a Spark data frame.
Harun, you're talking about like the stages, the Spark jobs, like
Yes,
what
yes,
happens exactly.
yeah.
I can give a little bit on what I understood.
Sure. Yes.
So I think the first thing is like reading it. You're performing the transformation, not the action, which is called the lazy evaluation. That's what happens. So the data frame is being prepped, for your Spark job, right? Then comes your actual action, whatever you're doing. So probably it's a count. You're doing a count, right? So that's when you're invoking the Spark, to the backend to work for you, on that one. And and we have looked at the how it works, in the stages. If there is a count, we have seen that so it reads the data, and then the shuffle happens, right? Then the shuffle happens, and then the count is actually displayed, in the Spark job, right? Uh, then comes the join. We have seen the join, how it works, between the two data frames. So we repartition the data again, and try to do a join between those two data frames. And we have seen how the Spark skips, some of the jobs, that have been done earlier already, right? And then it goes to again the shuffle and then join, and then finally gives you the results.
Right. Yeah. Awesome. Very good. I think, yeah, so we got the hang of that. Thank you, Shiva. That was awesome. So basically, yeah. So let me just run this, right? Okay. So just to reiterate what Shiva has already explained, right? So we have two data frames basically here as range, spark.range and spark.range. It's just generating some data, a range of data starting from 4 to 200, just list of numbers as a data. Yes, Pawan, you raised your hand. You want to talk about something? You have a question?
No, Harun.
Okay. Okay. So this is just like I'm declaring some data, generating some data within the using range function from 4 to 200. Again, this is just when there is there a Spark job here? Subbu, what is happening here? Can you talk about the step?
Here, Spark from the Spark table. Sorry, data frame 1 and data frame 2 defined.
Yeah. Good. Yeah, so we are defining data frame 1 and data frame 2 and pointing to some Spark function, range function that start from 4 and go to 200, skip numbers 2, like alternate every skip 2 and here skip 4 starting from 2. So is there data now here in df1 and df2?
No.
No.
That's good. Yeah. So basically it's just you are defining, like in any language, let's say you're defining a function, but unless you call that function specifically, nothing happens, right? So it's the same thing. So this is just the definition of what df1 will have, what df1 will df2 will have. Hey Nag, welcome, good morning. Okay, hi Sahil. Sahil has joined, Nag has joined, welcome. I guess. Hi. Yeah, so let's come back. So these are two data frames that we have just defined and pointing to some data. It's just a pointer. At this time, the function is not executed, the data is not generated, it's not there in the data frame because it's just, lazy evaluation. Now here, I'm just asking to get num partitions. Partitions is just basically metadata, right? So if you want to see how many partitions it will be when the data is generated, it's just a metadata. So you don't need to still run the job to get the metadata. So you can get, say, 8 partitions here. Now, df3, df4. Okay. So who wants to explain this part of the cell? Pawan, you want to?
Yeah, we are just saying that we want to create another data frame df3, which with 4 partitions. Like it has the same data as df1, but it will be having 4 partitions. At this step, we are again just defining the definition of df3. No data action is not involved. Only the definition is stored in the variable df3.
Okay. Now, let's say here you're saying we have 8 partitions, right? df2.
Yeah.
Now, df4, you are doing 5 partitions. So what happens to the other 3 partitions? So let's say, for example, I have 8 GB of data, okay? And my 8 partitions, I'm saying, have 1 GB of data in each partition. Now, again, you have to visualize partitions as a chunk of data, a block of data, which may reside on different machines in memory, right? Last time we discussed. So this your 8 GB of data may be distributed. Say you have 8 machines, which with one partition each. Just giving hypothetical scenario. So 1 GB of data is all distributed on 8 machines. Each machine is having 1 GB of data. Your 8 GB file is split into 8 parts, right? And each distributed on 8 machines. So each machine has 1 GB of data. Now we are not going at the level of what is the data, how that is decided, what data it should go to which machine and all that. So arbitrarily, it just chunks, splits into 8 parts and say on 8 machines. Now you're saying I'm moving all that data to 5 partitions. So what happens to 3 partitions, the other 3 partitions?
No, it will just have 1.6 gig of data in each partition.
Absolutely.
That 8 will be
Right.
this thing into 5. So each partition will have 1.6 gig.
Okay. So 8 partitions now will come 5 partitions, and then data is 1.8 GB. So how do you make that? What happens? So if you have 8 buckets of water, you want to move it to 5 buckets. So how do you do that?
Shuffle.
Exactly.
Shuffle data.
Sorry, Purnima?
Is the partition a physical like collapsing when it collapses? You no longer have those 3 partitions, right?
Yeah. So
Or
partition, just think of a block of data. That's it at this point of time. A partition is just a block of data. It's just like water in a bucket. So you have 8 buckets. The physical partitions will still be, the machine will still be there. Now, what you're having on that machine, the data in that partition, is what we are talking about. So the machine will be there, the number of cores will be there, the storage in that machine will still be there. We are not doing anything to that. We just say the buckets will still be there, but water in the buckets. Let's say I have 8 buckets and water in all the 8 buckets. Now I want to move it to just 5 buckets. How would you do that?
That is
You
I'm
shuffle,
telling.
right?
Shuffle the data,
You
right?
shuffle.
Yes. Yeah,
You
exactly. Shuffle the data. You take those extra 3 brackets and start, putting into other buckets, right? So that is shuffling. So you are moving data from one partition to other partition. So one machine to other machine, which have different partitions. Now all this data in 8 partitions is moving to 5 partitions. So that is exactly why the shuffle should happen. That's when the shuffle happens, right? So now you get the concept of what shuffling is and why it should happen. So this is one example of where the shuffling happens. So now, so any questions here?
Harun, I
No.
have a question.
Mhm.
When we repartition it again, so you said from 8, we will be repartitioning to 5, right?
Mhm.
Or 4. So will the data be distributed equally among them?
No, there are no guarantees. So more or less, but it's just closer. It's not exactly divided by this. It will be more or less similar. So it might decide in 8 partitions.
Mhm.
So already in 8 partitions, the data may not be equal. Okay. So let's say you
Okay.
have only 7.2 GB of data, right?
Okay.
So
Mhm.
some partitions may have 1 GB, some partition may have 0.5 GB, some partition may have 0.8 GB of data, right? So that's
Right.
not exactly divided by number of partitions. It's an arbitrarily it will decide to move more or less similar size of partitions.
Okay, I got it. Thank you.
Okay, Harun, just on that one question, I mean, I haven't tried it. Let's say, like, we have very huge file,
Mhm.
and I think 128 MB is the max partition, right? It tried to split based on that, right? So what if we try to repartition it? Will it ever throw an error if it doesn't meet that, or if it overflows that criteria? Have you ever come across through that situation?
Error when you're saying the file is too big.
When his file it's already has enough partitions, and we try to squeeze that file, but which exceeds that Spark like partition limit.
No, so it basically you can also increase the size of the partition. The default is 128 MB. You can go up to half GB or 1 GB or 2 GB of the partition size. It doesn't stop you having bigger size partitions. That's number one. Number two, it only throws error when it cannot fit something in the memory, and then it tries to spill onto the disk. So basically you have to understand, right? So when you are doing this partitions, this will be on the physical machines, right? So let's say you have only one machine which can store 1 TB of data physical, and then you have a file of 2 TB. That is when it cannot store on the disk size. So it reads in chunks and then processes it. But memory, it will not throw memory issues unless your data set does not fit into the memory and onto the physical disk. So normally the physical disk space is more than your data. It's just like your machine, right? So if you have like 512 GB of machine and you're trying to download a 1 TB of file onto your machine.
Yeah,
So it
I
just
mean,
say out of space, right?
yeah, I
Same thing.
understand that situation. Let's say like 1 TB we have and it's already created equal partitions, right?
Mhm.
So it's already did its best, okay? And then when we try to repartition, maybe it might throw an error, right? Because it's exceeds something. So that's what my
Yeah.
question.
So no, so repartitioning, it might, yes, based on the number of nodes you have and the size on that, yes, it might throw error. It's out of space. It cannot fit into
Okay.
that
Yeah,
part.
that's what I.
Yes. All right. So that is the repartitioning that we
Arun, one quick question.
yeah.
Sorry. Okay, so what would be the use case of doing a repartitions? Because we normally do the partition for making a performance is good. So what is the actual purpose of doing a repartition?
Yes, that's a good question. See, why we do repartition is basically so let's say you have a file and you have 200 nodes, okay? And then your data is split into 200 partitions, right? Now, each partition is just 1 MB of data or 5 MB of data, right? Now, if you want to do some calculation on that data, say, for example, I have 100,000 employees data, salary data, which is distributed on 200 nodes. Now I am doing a transformation on that to say salary equal to salary into some adding 10%, let's say increment. Now, how does Spark process that? It processes on each of the partition. It goes and creates a task and the task will run on each partition of data. So if I have 200 partitions, so I need to run 200 tasks to do the same operation on all 200 parts of my file. Now, instead, if I have less partitions, let's say 20 partitions, now I will only spawn 20 tasks to do that same on 20 nodes, right? So the overhead of creating more number of tasks to do the same job is reduced, okay? Or again, it's other way around. So if I want to join two data sets, now I have huge data on smaller machine. Okay. And that is taking a lot of time. So all my data is only on 10 nodes and the other 20 nodes are empty. Yes, Pawan, just one second. So, right. So I have 10 machines and all my data is only on 4-5 partitions. I have 40 cores and my 20 processor idle. I'm not using it, because the data is only on 5 partitions. So whatever operations I do, only 5 tasks get created, 5 nodes or 5 cores are working. The other 20-25 nodes are idle. So I'm not getting a good performance. Then what I will do, I will repartition that 5 partitions into 40 partitions. Then the overall process will be faster, because now parallelly I am processing all the 40 partitions. Each core is working on one partition to do the same task. Got it?
Good. Thank you.
Arun, in the first scenario, when you said that each partition has less than 5 MB, is there an optimal size per partition that we need to look into to be able to collapse the partitions?
Yeah, it's just a trial and basis, a trial and error based on your data, right? Your input data. Again, that's what you have to get optimum performance from your cluster. That's the whole thing. Now, how much data I have, how many cores I have, right? So based on that, you do your partitions. There's no fixed size. So default, it says 128 MB of partitions it creates. Now, if you have very huge file, but very small number of a small number of machines, then you go for big partitions. Now you have many cores, right? But smaller file, you can redistribute, you can create more number of partitions so that you get maximum performance. All your cores are engaged. So normally the number of partitions, let's say like it ballpark is like, multiples of your number of cores. So if you have 4 machines, each machine has 4 cores, that is like 16 cores. Now I can parallelly at a time have 16 tasks engaged. So you can do a partition size of 16 or 32 or something like that, so that it will process the first 16 and it's done. It will take next 16 and get it done. But if you have only 8 partitions, 8 cores will be working and the other 8 tasks will just be like idle. They just spawn and then do no work and then close.
So partitions is by data frame. You can create one data frame can be 10 partitions and other data frame can be 100 partitions.
Absolutely.
And the code can be in the same cluster.
Yes, absolutely.
And one more on a follow-up question.
Yep.
So do we have any kind of a data limitations while we are doing either the partition or the repartition? So we have to take this particular size of data while you are doing the partition. And also similarly, it's doing the same thing for the reverse case. So do we have any kind of a data limitations to do this practice?
No, that's what we were talking about, right? There is no data limitation. It's based on the capacity, the size, memory, and disk space that is available for you to distribute your data file to process, and the number of cores that are available to work on that. So you make a better judgment of, do I need more partitions or do I need less partitions?
Okay.
Okay, so when you do a join, for example, it creates 200 partitions by default. Of course, you can change that. But for example, let's say 200 partitions. But your data is small, only say 20 or 30 partitions you have data. The other 170 you don't have data. So what you do, those are idle. So what you will do, you will reduce the number of partitions after join, so that any subsequent transformations actions will only work on those 7 partitions. Okay. Yeah. So these are like, the business task specific things that we can, but I just wanted you to understand the concept of this. You should always try to visualize that your data is not at one place on one machine. You should always visualize they are distributed across multiple machines. The moment you say data frame, you should be able to visualize, yes, this data frame is on multiple machines, multiple nodes, not at one place. Then
Yeah.
it will be easier for you to visualize how you are doing operation. Yes, Pawan.
Mission and nodes are same, right?
Yes. Yeah.
And
For
each node will have
worker
a
nodes.
core.
Yeah,
Each node will have a.
Yeah, each node can have executors. Within that executor, you'll have multiple cores. Basically, the lowest thread or execution happens on cores, right? So the number of cores is equal to the number of tasks that can be performed at any given time in parallel.
In each node.
Or
out of those cores, one will be out of that. If it has 30 cores, then one will be master, or other 29 will be worker nodes, worker cores or something, or is that how it works?
So master is a different machine. Okay.
Okay, got it.
Worker nodes will be different machines. Of course, you can choose to have master also on one of the worker machine. That's again, let's not get into all those cluster configuration right now. But there will be some cores that are allocated to do your normal OS tasks, right? Operating system to run these things, some overhead to manage memory and all of that. And the remaining, all the cores will be available for processing. That's how you have to look at it.
So can you go to that compute thing here? See in this situation.
Oh, this is just one machine, right? So we don't have a cluster here. So Yeah, so what we get here is the configuration. If you see,
Harun, one question.
yeah.
Harun, so on the cluster, right? Okay, now we talked about like repartitioning, right? So
Mhm.
instead of repartition, if I have certain if there are some idle partitions, okay, which are not used, is there a concept of load balancing wherein okay, if there is a few in a data frame, there are few partitions which are overloaded and there are certain which are not used at all, okay? So is there okay a load balancing can be done to improve the performance rather than going for a repartitioning?
Yeah, no, see, the load balancing itself is the repartition. So
Okay.
if you have, that's what I was trying to tell you, right? So if you have 10 partitions and 2 partitions have huge data and the other 8 does not have. So typically what's happening is when you do any operations, there are 10 tasks that are triggered, but only 2 are worked upon, 2 partitions. The other partitions which have smaller data are idle or either just skipped or they don't do any work or very, very small work. So the time taken by the job, let's say is 10 minutes. So the first 2 partitions is what is taking 10 minutes. Now, if we do a repartition and have data distributed on all 10, so the overall time parallel execution, the overall time might reduce from 2 seconds to 1 second because now the data is distributed, all tasks are doing the equal work.
Okay, and this has to be done explicitly by the engineer itself, okay, by using the code.
Yes.
It cannot be done automatically.
Repartition, sorry, repartition will not be done automatically.
Okay, okay.
But there are some adaptive query execution that is some logical partitioning. When it does, it automatically senses and creates those data into those partitions. Whenever some shuffling or join that happens, it will try to get all of that to have mostly equal partitions. When you have see performance issues and when you actually see that some partitions are huge, some tasks are idle, that is when you can do that. Most of it, yeah, is now we have getting AI and we are getting new engine that is coming in that's trying to optimize all of this stuff automatically for you.
Okay, okay, okay.
So yeah, we can see here we just have 2 cores. Right? So we have only one machine, right, in the cluster. We don't have worker nodes and all of that. So this is one machine with 2 cores, 15 GB memory. So if we have 8 tasks or 8 partitions, what it's doing is the first 2 cores will do some on 2 partitions. Then again, it will pick up 2 partitions, then again 2 partitions and again 2 partitions. So it will like sequence 4 times it will do on all the partitions.
So Harun, when we say df3 equal to df1 dot repartition 4, we are saying that we are asking the system to create a new data frame df3 with the same data as df1 and with 4 partitions.
Right.
But as far as df1 is concerned, when we do a operation on df1, the data is still on 8 partitions, right?
Yes, let's see that.
Yeah.
So we do this here. We can do df2. So something interesting you should see. See, data frame is still on 8 partitions. Because that's what we said, right? A data frame is immutable. You cannot change a data frame, update a data frame on itself, unless you, whatever operations you do, it creates a new copy of the same data frame.
Yeah.
And sometimes it might be just the data is still there, but logically it's repartitioning into different blocks.
Okay.
So let's continue. We've spent some time. So you guys get this concept, right? Everyone? Any further questions?
One last question, I'm sorry. I'm not sure, and this might have already been asked in the previous classes, but I may not get a chance to. Okay, question here is, so do we have to, as a data engineer or the like whosoever is doing the task, do we have to follow a certain rules just to applying that? Let's say I have a transformation apply for the filter. I have a transformations to do the sorting part and all. So do you have to kind of follow a hierarchy to doing these activities while we are doing this process,
That's
or we can
that's
randomly actually? Okay.
that's a good question, right? So there is no rule that you have to follow any hierarchy, but you have to look at how you are optimizing. Okay. So by that, what I mean is, say if you are joining two tables, one is a very huge table and the other one is very small table on certain keys. And after joining, you are filtering out null values. Now, what is the optimum sequence to do that?
Sorry, come again. Sorry, I lost that last, but
yeah. So let's say I have two I have two data sets. Okay. So let's say employee and department. Okay. Now employee is 10 million records. Department is say like 100 records.
Okay.
Joining these two, that's a transformation. And after that, what I'm doing, I am filtering the data set to see where employee date of birth is null. So I don't want employee date of birth null.
Got you.
What is the optimum sequence?
Like we can join with, employee table, joining with the department table. Like while we are doing it, we are trying to filter out the null values.
Right. See, so now I have employee, say 10 million. Department is say 100. Okay. So my join DF will have 10 million again, right? So whatever it is. So let's say, let's say out of 10 million, 9 million have a department and 1 million I don't have a department, right? So let's say I got 9 million now after joining. Now out of this 9 million, let's say my date of birth is missing for 3 million. Now I filter this and then final filter data frame. How many rows I will have?
6 million.
Okay. So 3 million null values. So I will have final 6 million. Now, is this the optimum sequence of doing it?
Maybe we can filter the 3 million ahead from the set and then join.
Absolutely. So that is one of the optimization techniques. You have to filter out the data as early as possible. Now, if I do this filter here itself, when I'm joining, because I know that I will not be needing this null values. So my, if I remove this, this will become 7 million. Now I'm joining only 7 million, out of which say maybe 6.5 million, I'll find a match.
Okay.
So now you are reducing the join condition, the shuffling, the join, the partitions, repartitions, everything. You're saving 3 million records from getting across shuffling in the network. So you're reducing network IO, you're reducing memory, you're reducing the processing, right? So that is the sequence that is the optimum sequence you have to see based on your transformations. What transformations I have to do early, what transformations I can do later. That is the data engineer should think about.
Adding on to this, Harun, so let's say in the join operation, you look at the spark jobs and we look at the shuffle rates. Will we be able to determine that this is a redundant operation? We could have like, does the shuffle rates tell us anything at that point?
No, it would just say this much data is shuffled. It does not have the intelligence that this 7 million I have shuffled. You are using 7 million, right? The number of records it will not show in the DAG. Will just show that this data frame is shuffled. That is something that
Like in SQL, we have something called query optimizer, right? It will suggest you to create an index on something or create something.
All that is there. There is an adaptive query execution, which in Spark internals again in the advanced that you can do. Basically, how it goes is it creates a logical plan, it creates a physical plan, and then it adapts the optimum queries. It's called adaptive query execution engine that is there in the Spark, which will choose the best plan for you based on all the DAG that you have. It even dynamically changes based on the data. So once initially like this, you create a plan to join two tables, okay? And these are two large tables, for example. So it will choose some strategy like shuffle, merge, join I have to do. But after a while, you do some filtering like this, and suddenly the big table becomes very small. From million records, it becomes 1,000 records or 2,000 records, 10,000 records. Now it has intelligence to see, okay, one of the table has become very small. So let's change my strategy of join. So it will choose broadcast join instead of shuffle merge join. So all that is already, yes, built in. It's called AQE. You can look up. You can also do here if you want to see that. See, adaptive query execution is an optimization technique in Spark SQL that makes use of the runtime statistics to choose the most efficient query execution plan. So this is one of the performance tuning. Okay. It is disabled by default, but you can enable it.
Got it.
Okay. So this is, yeah, when we do the performance optimizations, these are the things that you have to look at. Adaptive query execution. What is the data? How much data you are seeing? Do you need to do repartition? Do you need to?
This is only for Spark SQL, not for PySpark.
It's the same. PySpark also underlying it will do Spark SQL under
Okay.
It's the same whether you do using SQL or whether you do using PySpark. The underlying execution will be at the Spark SQL.
Why it is disabled by default? I mean, generally you would want optimal, execution, right?
Sometimes,
So,
yeah, we don't know, right? Sometimes
yeah.
it's an option. You can just enable it.
Okay.
Sometimes you don't want, you want to force, you want to do what you have, what you want to do. You don't want to leave it on the system to do it. But it's just like a configuration flag that you can set. There are other strategies also where you can, just like in SQL, you can give hints. Use this join or use, you can force it. You can put the flag off. Okay, all those options are available. But yeah, so this is the, what I'm saying, the levers that you have to tune. So when you look at performance tuning, you can look at all of this, the join strategies. What is the strategy that your AQE is determined? So it is not able to decide based on the runtime data it has. So you can manually give a hint. Use broadcast. This table is small. I know that this table is going to be very small. So use broadcast. Don't do shuffle merge. So those kind of hints also you can explicitly give it. Okay. But yeah, I wanted to tell you that optimization, these are the things you have to keep in mind. You have to be aware of what kind of data you are dealing with as a data engineer. Is my data set going to be small after doing transformations? How do I do my sequence of my transformations? When do I cache my data frames? Which data frame should I cache? Will it help? Should I use memory or should I use disk? So all of those options. Then which kind of join strategy should I use? What kind of partition repartition number of partitions should I use? So all of these are optimization techniques. That's again case to case basis. It depends on your data basically. Okay. So you can just, this is old, like 2020, but there are a lot of changes after this. You can go ahead, you can go and check on that. Adaptive query execution engine that they have. Now again, we have something called Databricks has a Photon engine, which is rewritten in C++ to speed up this processing of execution of the SQLs. So that's the latest on the performance engine that runs. Okay, I think we discussed a lot of concepts. So I guess we are clear right now. And
I have one question. So another day, Srini mentioned about the serverless. So this whatever we discussed about these operations, lazy operations, and Spark jobs. So the mechanism will be same even if we go serverless, right? The basic mechanism will be same always.
absolutely, it will still be the same.
Okay, thank you.
Evaluation execution will not change. What will change in serverless is the elasticity part. See, if I want more number of nodes to be added based on my data volumes, it will elastically increase or decrease the, so you don't have to worry about how many cores I have, how many I have to repartition. So it will automatically decide, okay, your data has, 100 GB data. So ideally it should have 200 partitions. So I will scale up the number of nodes to have, 100 cores or 200 cores. And then I will run on that. So you are charged based on t-shirt sizing of the servers and hours number of DB units, Databricks units that you consume. So basically that's how elastic it will be, so that you don't have to worry about upscaling or downscaling that if you use the serverless. But the execution will remain same. It will not alter the sequence of execution. That still be lazy evaluation, still the transformations. It still only executes on action. It still do all the shuffling if required. So all of that.
Good. Thank you.
Yeah. Okay, awesome. Now so we have done this multiple times. So who wants to talk about this one last time? Let's not worry too much about it. As I said, when you go into your actual job, you may not need to do all of this on a day-to-day basis. It's just good to know how the execution happens, what is a stage in an interview also, right? So if there's, can you tell me about the execution of a data frame or a Spark transformation or action? So you should be able to know what is a stage, what is a task, when does a new stage come in, why shuffle happens, when does shuffle happen. These are the concepts that you should be aware of. Okay, and that will help you to reduce what do you need. Can you reduce the shuffles, because that is the more memory and processing intensive. So you have to if you have to make sure to use less number of shuffles as possible. You cannot avoid all the shuffles, but wherever possible, if you can, you should reduce that. Okay. So anybody?
What example we have to take, like which data frame we are executing right now?
This is the same that we are doing here. It's just a Spark, DF1, DF2 range.
Yeah, but the the DF3, is this for DF3 or which one? I mean,
This
when you
is
explain
the
what,
DF sum.
okay, DF sum. Okay. So since it's a lazy transformations, right? So first it goes to DF sum, then it sees like it has to get from the DF join. So it goes back to the DF join and goes back to DF3 data frame. So that's a stage, like, skip that part. And then when it goes to DF3, again, that is not the base. It has to go back to DF1. So from the DF1, it executes that, and then it performs the repartitions on top of that, right?
Yes.
And
Yes.
then it comes back to join, and then the sum happens at the shuffle, and sum happens at the last stage.
Right. Exactly. So these are all like, reading the data, then shuffle for the repartition. Then this is join here, shuffle query stage. This is the join. And after that, again, shuffle for the sum to get everything onto one node, and then do the sum of this. Okay. Beautiful. So now you got the hang of what happens in a series of transformations and actions. So I think we also posted what are some examples of transformations and actions, right? So anything that triggers a job is an action that you can, in that sense, but there is no hard and fast rule. When you do Spark read on, so something like this Spark range, this is not a transformation, but read, when you do on a CSV, sometimes it creates a job, but sometimes it gets from the metadata if you have from Parquet and other thing. Okay, but at high level, you can talk about saying that any filter operations, right? Any transformations like adding a column, doing calculations on the columns, dropping a column, selecting from the column, all of these are transformations. Group by is a transformation, aggregation. But when you come to action like show, display, count, or write to a file or write to a database is what your actions. And when you are expecting to see something immediately, so that is a action. Okay, so you can look at the cheat sheet that I think Srini has provided for the transformations and actions. Okay. All right. So I just want to give a 5 minutes break, washroom break. And when we come back, we will continue with the concepts. So I will continue the same thing and see how when we add a caching mechanism, how will the data frame execution all changes, and what are the different types of caching that we have. Then we'll do how we can do SQL on this, Spark SQL on the same data frames, just like PySpark, but just two things, and touch upon, like I mentioned, about join strategies a little bit. We may not do the actual example here, but just give you an idea of what the strategies are. And if time permits, we can do example, or we can take in the next class. Okay. Any last question on what we have discussed till now before going on a 5 minutes break? Anyone? So yeah, I think it's very good participation today. What do you think, guys?
Yes. Yeah, definitely.
Definitely, Harun. Yeah.
Yes, we are seeing a lot of participation now. I'm happy to see people participating, getting hang of things, getting the concepts, right? Nag, I haven't heard you comment.
Yeah, I'm listening. Yes.
Yes, okay, thank you. Chandra,
Huh?
Chandra, quite silent.
Okay, now.
How about Akshata?
Akshata also has been participating. Akshata.
Yeah, I'm good.
think Akshita is also participating. Yes, we'll ask more questions.
I think I need to more practice based on your
Yes,
notebook.
yes, absolutely.
Harun, one last question on this. You said that, okay, for example, we are doing a repartitioning, okay, from say uh, 8 partitions to 5 partitions, right? Okay, so there may be a scenario where data may spill over to the disk. Okay, in such scenarios, okay, how do you handle those errors or exceptions actually in the real time?
Beautiful. Yeah, very good question. That's what my next topic is going to be. When you do a cache, you have different options, how you want to do the cache. But even if you don't want to do, it will not error out. It will spill onto the disk if it is not there on the memory, and it will internally handle. It will do the calculations in memory. If not, it will again go back to the uh, it will go back to the disk and read the data back. So it will take more time for it to do both memory and disk, but it will not error out unless if it goes beyond the disk space, then it errors out. Then you know, right? Obviously, either you have to increase the number of partitions or increase the memory, one of these two. Increase the size of the t-shirt size of the machine that you are processing. So if you have a uh, M or L machine that has 2 TB of space, and your partition is taking it should not ideally 3 TB or something, then you increase the size of your machine to 3 TB, or you increase number of partitions so that you add another node of 1 more TB so that you'll have more partitions to work on. So either one of these two.
Yeah, Harun. Just a follow-up question here. Since Databricks is on either one of these clouds, right, on GCP or Azure or AWS, so this scaling up and scaling down of the partitions can be handled or automated, right, at the cloud level at least, or is that okay? Everything has to be checked by the data engineer, and it has to be
No,
like,
no,
yeah,
you don't check all of that.
yeah.
Basically, again, you will have options when you are configuring your clusters, when you're buying the clusters, you have an option for auto scaling.
Yeah, that's what I meant. Yeah.
Choose auto scaling, it will automatically do all of that for you. Again, serverless is also one of the options that we were talking about earlier. So
Right.
don't have to. So those were the olden days before evolution of all of this, that you have to specifically choose. Again, it's a cost matrix, right? I am okay to run my job for 2 hours. I'm not in a hurry, bad job, but I want to do it in less cost. So I will choose smaller machines and a small number of, more number of partitions on those machines. And I'm okay to do it. But say it's a credit card kind of a data, I want immediate, results. Then I will choose a higher configuration to run it faster, seconds. So it's all like business case, use case basis.
Yeah. Clear. Absolutely clear. Thanks.
Absolutely. Okay, guys, just give me 4-5 minutes. We will be back. Okay. Hello guys, welcome back. I hope everybody is here.
Yeah, Harun. Yeah.
Yeah, nice. Okay. All right. Welcome back. Let me share my screen. We will continue with our lineage of transformations and actions and see what is the next. So I'll show you some slides, basically again from the internet images, just to reiterate the concepts of some of the questions that you have raised today as well. So let me share my screen. Okay, so we have seen this, you know, how the transformations are all chained, and when we have an action, it triggers the job to run all of this. So there's another concept in this called caching. Okay, so let's go and see how caching impacts our transformations and actions when we do any of our jobs. Okay, so I have a CSV file here. Basically, it's the same CSV file we are talking about. So the Amazon data set. So I'm just reading all the CSV, all the data from the CSV files. So here I'm reading it. See, there is a Spark job, Spark jobs that are triggered to read all those files. Okay. Basically, we know this when there is a read from CSV, it will trigger Spark job to read the data. And also because we are saying infer the schema, based on the data. So it has to scan the file and infer that schema, take the header values and all of that. So this part is clear. Now what I'm doing here, I'm creating a df1 as data frame dot select, df dot select, name, category, subcategory, link, and then doing some transformation here. Again, same, removing the characters and casting it to a double. This part, everybody's clear? Everybody's clear with this part?
Yes.
Cool. Okay. Now I'm creating another data frame which says df2 is basically data frame 1. I am filtering out the discount price greater than 10,000. Only I'm taking these values. df3 is df2 with column, adding a category column, which is concatenation, adding main category and subcategory. Then df4 again saying more discount from df2, a discount price minus 5,000, another column. df5 is another data frame, df2 dot with column, name, image. So I'm concatenating the name and its image. So these transformations are not meaningful. These are meaningless transformations, but just for the sake of example, I'm just taking it. Okay. Now display df3 dot count, df4 dot count, and df5 dot count. So I want you guys to give me the lineage of this. So I will ask Akshata to give me the lineage of all these data frames. So Akshata,
Yeah, sure.
df3
So
dot count, what is it
yeah,
dependent
it's dependent on df2.
on?
And then also yeah, we are adding a new column which is like concatenating main category plus subcategory.
Right. So what is
And
df?
then yeah, and then it'll df2 is like we are filtering out discount price greater than 10,000.
So it's dependent on
df1. Yeah, it will go to df1.
So let's from df3 goes to
DF1.
DF1. Okay, so do we have, how is DF1? Where's DF1?
Yeah, so DF1 is like we are selecting these columns from the data, which is like name, category, subcategory, and then the image. And then we are also doing a transformation here with the discount price. And then casting it to double, and then naming that as a discount price, naming the column as discount price.
Awesome. Awesome. Very good. So what is it dependent on? DF1? Which data?
DF dot
Yeah.
select.
Yeah. So this is on, so it needs DF to do those operations, right?
Yeah, yeah.
And DF is basically Spark.
The Spark read function.
Is basically the Spark read. Awesome. Now let's do the same thing for DF4. Okay. So I have DF4. So DF4 is, who wants to give me the lineage for DF4? Yeah, you can continue, Akshata. Let's see. DF4 is basically
it's dependent on DF2.
Okay. So once this is DF2, it will be same, right? So DF2 is dependent on DF1. It is dependent on DF. It is dependent on Spark read, right? So it's the same thing. Lineage here. So it's dependent on DF2. Oh, sorry. Okay. Basically, DF5 is also on DF2. It's just a different transformation, but ideally also dependent on DF2. Okay, so this is data frame 5. The lineage is same. Data frame 5 is dependent on data frame 2, which is again dependent on basically here DF1, and DF1 is based on dependent on DF, and that is the Spark read.
Spark read.
Okay. Awesome. So now we got all of this lineage. Now let's run this and see what's happening. So we just executed the data frame, right? We read the job. So there are 4 Spark jobs here that we read. Now DF1. Okay. So what is happening? I run the DF1.
Yeah, so
yeah, go ahead. Anyone? So I just executed DF1. Chandra, talk about this.
It's a lazy operation.
We are just defining it.
Absolutely. Yes. We are just defining it's a lazy operation. DF1 is here. So I'm also defining DF2, defining DF3, defining DF4. Nothing happens. Okay. See, I have to observe this. What is the time it's taken here? Less than 1 second, right? So this time we also, let's focus on this. How much time this has taken?
18 seconds.
18 seconds.
18 seconds to read. Okay. So all of these are just definitions taking less than 1 second. Okay.
Harun, I have a question.
Yeah, sure.
So when we do this, will the Spark generate DAG at this point of time?
No, right? So it's just a instruction. The DAG.
Okay, so until an action is triggered, that time the DAG is generated.
Yes.
Okay.
Even if it is, you cannot see it now because you don't have a job that shows the DAG. Right?
Okay.
So why? Because see, you have created this transformation, but you don't know what other transformations are created down the lane, right? It does not have
Okay.
all the information. Down here, you might have again dropped this column. So if I generate a DAG here with this column, you might have dropped later. So which means it will take the net. So if you add a column and drop the same column, it will not even consider that column at all, because there's no point, right? So it kind of consolidates all the transformations. So that's why the DAG
Okay.
is created, or the DAG is regenerated just before execution of the action. Okay.
Yeah. Thank
So
you.
this is, yeah, less than 1 second. Now here is the action. I am displaying df3.count. So when I trigger this, what happens? Chandra Garu, you still here? Are you on mute? I'm not, I didn't hear your voice today. Okay, I think he's mute maybe. Anybody else who wants to
Now it will process that DF3 and it will display the jobs.
okay, so when we do this df3.count, df3 is dependent on df2, should calculate df2, then should calculate df1, then data frame, which is a df, which is a spark read. So I run this. Okay. So I think this is already what's happening. Okay, so I will tell you why I did that, but let's see here. We have df3, I executed it. Now it's triggered the Spark jobs. Okay, now how much time it's taking? 14
Okay.
seconds. Okay, please observe this. So df3.count is taking 14 seconds. Now I want to do df4.count. So df4 is dependent on df2, df1, df, and then spark rate. So now observe here. It's again triggering the spark jobs to calculate. And how much time it has taken? 12 seconds, right? Now I'm doing df5. It's again 12 seconds. Okay. Now, why is it taking 12 seconds, 12 seconds? All of these data frames is because it is doing all of this again. If you look at the Spark jobs here, df3, if you go here, see it scan the CSV file and then the whole generation to read that and exchange the you have to do the shuffle for transformations. You look here, this is already calculated in this job 66 here, and then it is doing a shuffle query and then whole state code gen. If you see here, again, it does the same. Read the file and then do the same transformations on that. Right? So every time you invoke any of these actions, it is going back and recalculating all of this. So don't you think this is redundant? Because df2 is there. Why are you again doing df1 data frame? Why are you reading the file and again every time I'm using this? Right? So what I will do instead is I will cache this data frame 2. And whenever I access the data frame 2, I will use it from the cache. Okay, so that's what I'm trying to do here. So what I'm doing here is df2 dot cache. So I'm caching this data frame, and then I'm invoking this. Again, cache is also a lazy evaluation. Unless there is an action, it will not calculate that, cache that. So I'm doing a df2 dot cache and then triggering df3 dot count again. Now let's see what happens. So again, it has done the same Spark jobs. It's calculating again df2, df1, df, Spark read, everything. See, again, there is a scan CSV, whole stage code gen, something is happening. I'll come to you. And then it does, this stage is done, and then this, you're reading it here. So how much time this has taken?
16.
16 seconds. So almost same time, 12 to 15, 16 seconds, right? So let's see. Now I'm executing df4 dot count. How much time it has taken? Less than a second. So you see the jobs. You see here, same thing the DAG is, but you see here a green button. Wherever there is a green button, it shows that it is a cached in memory. So here there is a in-memory table scan. So it is just going to the memory and reading it from the memory. It is not going to recalculate, read the file and everything. See here, this is what it is. It will give you the what is the data frame that is cached here, all those details. But wherever there is a green button, which means that it is reading from the cache, not recalculating the data frame. So that's why if you see, if it is less than 1 second it has taken. Now I'm doing data frame 5. This is also less than 1 second. Okay. So basically, if you see the DAG here also, it has the in-memory table scan. So if you go here and see this DAG, there is no in-memory table scan. See? Right? So now, just by...
Why is that df3? You put df2 in cache, right? And df3 is also dependent on, I mean, he's from df2. Why df4 and df5 only got...
No, df3 will also get. So because this is the first time, by that time it is not cached yet. Okay, let's see. Let's do a df3 dot count here again. Oh, sorry, not here. So this is cached now. df5 is done. Now I will go here and say display df3 dot count. See, less than 1 second.
So I understood first time if you give df2 dot cache, it won't calculate. Whenever
Yes.
we perform that df3 or df4,
Action.
the action will perform, then it will calculate. That's why it will take time. The next
Yes.
performance, it will take 1 second, less than 1 second. Okay.
Exactly. Awesome. So you're getting the concepts very clear. So it may not, it cannot, it does not need to be df3 dot count. It can still df2 dot count also will work. As long as your df2 is triggered and cached, any action that will trigger df2 and df2 is cached, it'll cache that data frame.
So it will cache only after the action, you're saying?
Yes, right. So only when there is an action, right, to trigger that df2 is calculated, then it will cache. Without calculating, how can it cache? I want to cache the results of a data frame, I have to execute the data frame. To execute the data frame, I need an action on that data frame, right? Yeah. So we're just triggering this cache part. That's it. To trigger that, we are using an action that will calculate
Okay.
the DF2 and then cache it.
So no, even if we cache it or no, the execution, the number of jobs will still remain the same. It won't change.
Yeah. So the job will not change, but how it reads the data will change. Okay. So it is reading from in-memory table scan here.
The DAG won't change.
Yeah, the DAG won't change because it's just showing the dependency, right? So how DF2 is calculated. Now, instead of doing a full scan at the file level, it just does the in-memory table scan. So that's what it shows here. So here it says scan CSV, but what it does is it reads from this in memory. Okay. Now the question is, okay, we are caching. Now we'll go back to our questions today. What happens if there is not enough memory to cache? Right? That's the question we had earlier. Now, what happens if we don't have the cache? So basically the cache, it gives you two options to cache. Okay. So that is data frame. So if you see here, df2 dot cache. Okay. So this is caching. Cache by default is in memory only. Okay. So it will store all the results in the memory. Now, if it does not fit in the memory, then you get out of memory errors. So then what you do is, it also gives you another option to cache called persist. So in persist, you can have different modes. Okay, how you want to cache this. So persist, you can do memory, you can do memory and disk, you can do disk only, you can do memory serialized, you can do disk serialized, you can do memory and disk serialized. So these are various options that you can use to cache your results. Okay, these are most of it intuitive. Let me I'll let one of you guys to take a shot at this. DK. Memory and disk only. Can you try to guess?
Yeah. I mean, memory means it keeps it persists in memory and it not to the disk, which means it is available only for the job and not for I'm thinking, right? And disk only means it does persist to disk, but won't be available in memory. I don't know.
It's RAM,
Right?
using RAM versus hard disk, right?
Yes. Definitely.
Yeah.
Yeah, you're close. You're close basically. So memory is, as it says, memory only. It stores
Yeah.
the data frame entirely in memory.
Memory.
Memory and disk is basically is a hybrid. Okay. So what it does is, for example, I have a 10 GB data to be stored in memory. Okay. And I have say 5 GB memory. So what it does is it stores 5 GB in memory. Okay. And the rest 5 GB, it spills onto the disk. Okay. 5 GB in memory and 5 GB to the disk. Now what happens? So disk does not mean that it's going to permanently store on the disk. It is again temporary only, because once your job is done, it will delete everything in memory and also on the disk, whatever it is, data that is. Because it's only
Disk means
stored
DBFS.
to recalculate. Sorry?
Disk means you mean to say the DBFS file system, right?
Yes, yes. Not DBFS. It's on the machine nodes, whatever you have on the local node, local memory disk, it will store.
Okay.
It does not persist onto the database file system. No, these are all,
Okay.
this is still, even if it is on the disk, it's still temporary. It's like temp files, for example.
Okay.
You know, when some processing is happening on the system, it will create some temp files in the temp folder. But once the program is done, it will delete all those temp files.
Okay.
Right? So the same thing on the disk, 5 GB, and here 5 GB. So whenever you want to read the data frame, again, it will read half of it from the memory, and the other half, whatever it is there on the disk, it will read from there. It will increase the network IO because it has to read from the disk and write to the disk. So that will add some time in the performance, but still it's better because 5 GB you're still in the memory and 5 GB to the disk. You can do disk only, which means it will not store in the memory. It will write all 10 GB to the disk. Okay. This, it may look, it's not very optimum, but let's say your job is memory intensive and you don't want to have this huge data in the memory for other calculations that we are using, and you have super fast disk like SSD or something, then you can choose to have disk only. Now, these the same things with additional of serialization and deserialization. Basically, it can serialize your data, convert into serialized format and write to disk or memory, and then read it back for any operations. If it needs to deserialize, it will deserialize. So that will also
Serialize
add
means
some more.
sequence.
Sorry?
Serialize means sequence. What is it?
Serialization is like converting the data into numerical or machine readable format.
Okay, got it.
And serialize and deserialize. So basically, it will also add some time to serialize and then deserialize it, but it will reduce the space when it stores on the disk or in memory. So it's just a trade-off. Okay. So these are the different modes I was talking about here. So memory only, serialize, memory and disk serialize, disk only. So these are all the different options that you do for caching to persist. So whenever your job is running and it senses like, your garbage collection or whatever, it senses that you're not using this data frame anymore in the calculations, it will automatically remove it from the memory. But if you want to do it yourself, you can just do df.unpersist. So it will remove it from memory. So that's why, like, when I was executing this, I had run it previously. So that was already in the memory. So when I ran it, it immediately took less than 1 second. So I had to remove it from memory to show, to do the without memory, how it runs, without caching, sorry. So unpersist will remove that data frame from the memory, delete it from the memory. So you can explicitly call and remove it from the memory.
Can we do the same thing for cache? Can we remove the cache, or also if
Yeah,
the
it's both the
cache?
same. Cache and persist is same, basically.
So if
Cache
good.
is same as persist memory only.
So if I have a notebook where you have defined a cache for DF2, and if I want to use the same data set in a different notebook, which is actually DF2, but I would declare it in a different data frame, would it be shared? Like the scope of this cache would be shared with the other notebook as well?
Your variables are not it's not the scope, right? It's a scope.
Okay.
You can only access the data frame declared calculated here within this notebook. If you want to use it in a different notebook, that's when you have to write it to us, create a table, and then write the data to the table and read it from that table. Okay.
I'm not talking about reading the data from it. I'm just talking
Yeah,
about
data
how
frame, data frame is just data, right? So you cannot access this data frame in another notebook. It's a scope.
No, but DF2 in turn goes to the main only one data frame. It's a file. Like basically the source of this data frame 2 is a file. So we are saying that cache the data in that file. And I'm using the
No,
same
we are
file.
not caching the data in the file.
Okay.
We are not declaring any files here. It's just how Spark internally manages to store that in memory, that chunks of data that it is calculating. We don't have any external source that can read into the memory what data frame 2 is. So data frame 2 is a local variable within the scope of this notebook.
Okay.
Okay, so it cannot be accessed unless there are two options, unless you write the data frame to a file, df2.write to a file. That is when it will go into DBFS file system, and that file you can access from other notebook or whatever. Or you write it to a database table, catalog table, df2.write as table, and then from other notebook you can create and read that. There is another thing called global view, so which is not much. It's like create
Right, but
global
we
view.
are not taking advantage of cache in those options, right? We are writing it again, and then if you have to read the data, we again have to cache that data set, but we are not taking advantage of the cache that we created here. So
So
you're
the
saying
cache
that
is, see, think of it as a program. Okay. So this notebook is one application running. All the memory is of this program is only available to this program. If you are creating another notebook, it's another application, another instance of the program. It has its own memory area, right? So you cannot read from one memory area into another memory area. It will corrupt, right? So I am doing some transactions in DF2 here. Somebody else, some other data frame says df2.unpersist. Now what do I do? Or he does some transformation in another notebook and drop the columns
makes
from it,
sense.
right? So you cannot allow any of those to impact your current program unless you are persisting to either database or files that they can also read from other applications.
But only thing is like if you're invoking that notebook 2 from notebook 1, yes, in that case, we can still use this data from cache, right? That's the
You
difference.
cannot invoke a notebook from this.
We can write %run.
%run is basically another to create. It's just like a sequencing. Sequencing your notebooks in a pipeline. Yes, you can run. It's again like triggering another job from this, but I don't think you can still share. That's something I should.
Is it? Okay.
Yeah.
I was thinking in a different way because it's still same program, right? But it's a different notebook. It depends, like same program, different notebooks, or different programs, different notebooks.
Yeah. So when you run an application from another application, it's just creating its own Spark context, its own memory. It's not sending from there. But yeah, that's something that I should check. I mean, I haven't used that basically. But yeah, that's the concept. That might be a rare scenario where you share the objects across notebooks. But this is the cache. So you guys are clear. So basically how in a scenario is if you have in different notebooks when you're doing a workflow, that's when you sequence your notebooks. So my first notebook may be like, just reading from source and writing to bronze. So I will keep that notebook separate only up to bronze. And the data is persisted to bronze layer at the end of that notebook. If it is successful, then I go to a notebook that does the transformations on the notebook, data cleansing, data transformations that will read from bronze and write to silver. So that is the scope of that will help you to manage, right? So which notebook is doing what, where it has failed. if I chain it within the notebook, it will become clumsy in maintaining things. And so when you do a gold, so there might be multiple notebooks branching out. So once the silver is completed, there might be 4 or 5 different notebooks that are doing different aggregations on the silver and writing to different tables on the gold. So that's how the DAG, that's how it's also called a DAG, and basically in Airflow. So how you sequence the notebooks, that is different from this. Don't confuse again, sorry. So basically how you sequence your jobs or notebooks to run in the pipeline. Okay. There might be some rare case where you want to initiate, but that's not standard. Standard in the sense that not do regularly. Okay. So things clear about caching and using that. Hari, Venkat, any questions?
One question from my end.
Yeah.
Okay. When you're actually doing the cache, so do we have to use the same thing? Do we have to use the cache for same kind of operations for the other dependents? Or can that be used for the different operations as well?
Oh, see, you can use different. See, basically, you have cached called a DF2, right? Data frame 2. Okay. Now, let's say I have DF3. I can cache DF3 also, which is basically dependent on reading DF2, but it has created its own different data frame by doing some transformations on DF2. So I can cache DF3 also. Then it won't even read DF2 from cache. It will directly read DF3 from cache if there is any other operation that is dependent on DF3. Because DF3 is already cached, it does not need to read DF2, DF1, DF, or calculate or read the cache from DF2. So you can use it for any operations, but all you have to be careful about is which data frame you are caching and how you are using it. Or if you have transformed that data frame again after caching, so it will invalidate the cache if you're reading it later.
Okay. Can that also be used for the other aggregations as well? Since we have taken only count part, like if I wanted to do a different kind of a calculations, can that be useful?
So it is not dependent on what calculations or aggregations you are doing. You are only
Okay, got
caching
it.
data frame.
Got it.
Okay. DF2 is cached. You can do any aggregations, any actions on DF2, it will still read from the cache, not count. If you want to say join, if you want to do group by, whatever you do, it will just read it from the cache.
Got it.
As long as you are doing that and storing it on another, you are creating a new data frame. But if you are doing transformations on DF2 itself, then that cache you said, right? It will.
Yeah, it is DF2 is now you are pointing to a new data set after
New
transformation.
data set, so you need to
Which is
cache
not
it
cached.
again.
Yeah, you
Yeah.
have to cache that. Yes. Because the pointer is now moved. Whatever the data that is cached, that is no longer pointing, DF2 is no longer pointing to that. So DF2, you have used the same variable name to repoint it to new data set that you have transformed. That is not cached. So what the garbage collection will do, it will go and remove that from the cache because nobody is pointing to that memory anymore. Your DF2 is now pointing to a different data.
So ideally, you cache it when you are not changing it anymore, right?
Yes. You cache it when you're not changing it, but then you have to see again, am I using that data frame in multiple operations? So if I'm using DF2 only once, then it doesn't make sense because by the time you have cached, you have already calculated it, everything, used it. but you cached it, but you're not using it later after caching. So it doesn't make sense.
Right.
Saying you are using it after caching, say multiple things, multiple times for different purposes, then you can cache. For example, you have orders data that is coming in and you cache the orders, then you are using the orders both for calculating the sales, you are using it to calculate the inventory, you are using it to calculate the deliveries. So if you're using it multiple times, then you can say cache that orders and then use it in multiple calculations. Okay, all right. I think, yes, we are clear. I will also publish these notebooks. So before wrapping up, so I want to touch upon, I want to just, okay, let's review this. We also talked about this. So this is again an image I got from the internet. Spark performance. So what is it talking about and what we have discussed today? You can see this, right?
Yes, sir.
Yeah.
So these are not all of them. It's just few of the things that you can look at, right? Use the Apache Parquet file format. So this is by default Databricks does. Databricks Delta. It automatically uses Parquet file and it uses Snappy for compression. Okay, so that is taken care. Number 2, maximize parallelism in Spark. So this is what we were talking about when we said partitions, right? So see here, it says maximum partition bytes is default to 128 MB. Try values between 50 MB and 1 GB. And then shuffle partitions is default to 200. At least number of CPU cores. Just give me one second. Laptop is stuck. Okay. You can still see the screen, right?
Yeah.
Okay.
Yeah.
I think my MacBook is stuck. I cannot change it, but yeah, I cannot see the last part of it. It's hidden. At least the number of CPU cores, then test by, can anybody read that part? I can only repeat that.
Test by increasing.
Okay, test by increasing. So this is also, see, it was a coincidence that we already touched upon all of this. You guys are smart enough to bring all of this today. I had actually thought of talking about this at some point, but yes, you already have brought these questions, which is a good sign. So 128 MB is the default partition size, but again, you can change the partition size to have 50 MB up to 1 GB based on your file size and number of CPU cores that I was talking about. If you have more number of cores available, you can go smaller file size, so that all your cores are being put to work and it does faster. If you have less cores, then try to have bigger partitions so that when the task runs, it does more work than if you have 10 jobs for one core that are lined up. So it has to do sequential. So it's just kind of a trade-off that you shuffle partitions. Also the same thing. Once you shuffle, it can be 200 partitions. If you have 200 cores, fine. If you have 20 cores, define the shuffle partitions to 20. That when you shuffle, again readjust the data into only 20 partitions so that my cores can work on that, or 40 partitions, whatever, right? So that's the trade-off that you have to do, maximizing the parallelism in Spark. Beware of shuffle operations. That's what I told about. So whenever there is a group by, you do joins, you do, there is a shuffle operation that happens, right? Memory is 1 GB. If the driver needs lot, because it has to get all data to one place, then again split, move it to other partitions, other nodes. That is something that you can do, giving driver memory, how much memory it needs to do that shuffle partition. But you have to avoid as much as possible to do the shuffle partitions thing. Then number 4 will come to it. Number 5 is cache. So this is what we just now covered. We looked at it. Data frame dot persist. What is the storage level? Is it memory and disk? Is it just memory? It says memory and disk serialization, which offers a good trade-off. If you have a, you don't have to put everything in memory. You can put some memory and some disk with serialization. It will give you, so it again depends on case to case basis, how much data you have, how much memory you have, to do the handle that caching. Manage the memory of the executor nodes. This is not much. It'll obviously mostly it is automatically doing this. But again, it is like scaling. If it is going out of memory, your data does not fit in the executor memory to process, then you get that out of memory errors, which you can solve by doing scaling up or scaling out, adding more nodes or increasing the machine size, but auto scaling will take care of that. So number 4, broadcast hash join. Okay, that's what I wanted to briefly touch upon, but I think we are at time right now. Broadcast join is basically what there are 3 types of joins. I'm not able to even.
Try escape.
Yeah, that's what I'm trying to do. I did. It says.
Or kill the process and reopen it.
Okay. So basically Spark uses 3 different strategies to join. See, we have types of joins, which is inner join, left outer, right outer, all those things that we have already seen how we do the joins, and people from SQL background, you should have already be aware of that. On top of that, it is a strategy how Spark wants to do the join, perform that join basically. So it has a broadcast hash join, it has shuffle merge join, it has sort merge join. Okay, so join strategies: broadcast, shuffle hash, and shuffle sort. So these are the images again from the internet, just for us to understand the join strategies concepts. So remember when I said our data is distributed on the nodes, right? So if I have 2 data frames we talked about the other day, employee data, if I have million records, so it might be distributed, say 100,000 on each machine, on 10 machines. So each node may have 10,000. Department data, 100 records. Again, data frame is distributed. So each node may have 10 records. Okay. Now, when I'm joining employee and department, the department number on node 1 may have joining the employees on node 6, 7, 8, 10,000 on this, 50,000 on this, 30,000 on another machine. So basically you have to shuffle everything by keys and have all that in one machine to join. Suppose out of, if it is IT company, right? And say out of 10,000 employees, 9,000 belong to IT department, and 1,000 out of 1,000 maybe say 100 for HR and say 100 for admin, something like that. Now, when I'm shuffling it, it wants to coexist. So what might happen is all the out of 100,000, 90,000 employees belong to IT will come onto one node, one machine, where the department ID record will come onto that machine. And other nodes may have, HR data on one node, admin data on one node, but they have only, say 100 records, right? So that is unequal distribution. Now joining, there is a lot of shuffling that has happened. Instead of that, what Spark does is it will see if you're joining two tables, it will see if any of these two tables is smaller in size. Okay. Because the departments has only 100 records. It's a small table. And then you are joining with employees, which is say 100,000, relatively large table. So what it will do is the 100 records of department data, the smaller table, it will create copies of that data and then ship each copy to the nodes. So instead of one copy trying to shuffle and join with other nodes, each node will get its own copy of that smaller table. See here, worker node, there is a large data frame, which is say our employee, partition 0, partition 1, partition 2, partition 3. Now the small data frame, which is our say department, 100 records, it gets a copy. The same copy is shipped to all nodes. So this is the entire data frame that is shipped, all the data in memory. Now what it will do, it will join within this node. It will join within this node. It will join within this node, and it will join within this node. Now we have joined data on all data frames. Done. Simple. There is no shuffling here. There is no data shuffling. Right? So it saves your IO, it saves your memory, it saves your processing time. So this is the best join strategy. However, the catch is that one of the tables should be small and the other can be small or big. So it should fit the copy of the data frame, entire data frame should fit on your worker node in memory. So your worker node memory, say, is 10 GB, right? And your data frame is already taking 8 GB. So the smaller one copy should be less than say 1 GB to fit in there. So normally there is a threshold that you can also give. Say my smaller data frame threshold is if it is less than 2 GB, consider it as broadcast hash join. And as I said, you can also give hints how you want to join. We'll see that, try to do that in an example in the coming classes. But this is the concept. The standard other concepts it does is shuffle hash join. Basically, it's the same standard that we discussed. You have two data frames. It will try to shuffle data based on the keys you are joining so that the data for the same keys coexist on some same worker. And then it will do the hash join on those things, on those machines. So there's a shuffling happening between this. The shuffle sort merge join is basically another variation of this. It still does the shuffling of the keys, but what it does is it will also do a sort on the keys so that the join is easier. So there is a sorting phase also involved in the joins when you do it after shuffling, and then it will do a join. So basically shuffle, then sort, then merge the join. That's shuffle, sort, merge. And this is the default join that Spark will consider when joining the tables. And sometimes it's intelligent enough to do the broadcast. But if it is not, you can look at it and then explicitly say, try to give a hint, use broadcast join. Okay, so this is what I wanted to briefly touch upon. We will do more examples. But then there are two other things. So one, trying to see these join strategies. And then the other one is we do SQL. So tomorrow we'll try to do this same Spark data frame transformations using the SQL, that what we are doing with PySpark, and see if we can do this example tomorrow or probably by Wednesday if possible. But I encourage all of you to start practicing, the notebooks. The data is there. We'll be publishing the notebooks as well. So try to do the more hands-on. Okay. So we are almost on time. Let's take some feedback, some questions, how we are doing.
Today we have a lot of concepts compared to the previous classes.
Mm-hmm.
Yeah, a lot of cache and the previous concepts.
Excellent.
It's a good.
Excellent.
It's a
DK.
more intensive class today, I feel.
Yes.
Yeah, it's very good coverage. Please, yeah, share these notebooks in the Google Sheet and also all the links on Thursday class and today's class also uploaded.
Sure.
Thank you.
Definitely.
And among students, anybody want to have a separate practice session with our teacher? If anybody interested, we can form a separate group and we can practice.
Yeah, I'm interested in it.
Yeah,
Yeah,
I'm
I am
also
interested. Yeah,
interested.
yeah, we can. Yeah, we should.
Mhm.
Okay, let's form a group.
Yeah, sure.
That way we can each motivate it. So
Yeah.
okay,
I think that
right.
session would more you guys share and do the work, and then we can support, see if there are any issues there.
Yeah, any questions, we can come back with questions.
Yes, absolutely.
Okay, right. Thank you.
Thank you. Yeah. Amrita, Sahil, how did we do today?
Yeah, very informative session,
Yes.
Harun, and I learned a lot about Spark internals and I never know what's happening in the background. Today, I come to know that that what happens.
Awesome. Very good. Yeah.
I think Harun, I think we are really getting into like real world. What you do out there. All these, need to understand definitely if we in the when you get into doing something real. So.
Yeah, absolutely. Awesome.
Yeah, Lakshmi Prasanna, what is your feedback?
Yeah, obviously everyone mentioned that it's great, it's a concept, but only one thing, Harun, which I would feel is like, for experienced people, at least they know, but for the newbies and all, right, maybe we can emphasize like these are good to know. We don't do this
Yes, absolutely. Yeah, you don't want to get
purpose or something like that. Yeah, so that they don't get confused or they don't worry that, oh, I need to know how to do this and all. That's what I feel.
Yeah, it's fine. So these are the concepts to know. That's as I said, right? To talk about it in any interview questions, when you're discussing with somebody, if you use these terminology, it'll give you a lot of weight. So, hey, these guys know what they are doing. They understand the how Spark works, how they're doing, not just writing the notebook and doing transformations, but they know what is also. They won't ask you, show me how this join is done in the DAG. If you can just say, yeah, there is a DAG and it kind of chooses the strategy, which tables to join, and then it does a sequence of the DAG, and then we cache, it will read from the cache. It doesn't recalculate everything, and it is a directional. As I click, it does not go back. It keeps all the transformations as instructions, and only when you call an action, it gets executed. So if you just talk about this, done. In 2 minutes, they know, oh, these guys know a lot about all Apache Spark and Databricks, right? But what you do when you are actually doing this, lot of things under the hood, Databricks or Spark will automatically do it for you. You have to just know what transformations you have to do. But that you have ChatGPT, AI. AI will give you what you need if you know the, if you want to know what kind of transformations. So if you do go here, it will automatically tell you, see, it will generate the code. You want to do SQL, you want to do transformations, what kind of transformations, so data frame, you do transformations, you do %SQL, how I write a SQL for that. All of this. So the syntax you will get from AI, the execution performance, Databricks takes care of. So 60% is already taken care of. So you have to just know that 40% how to connect these things, right? So you should know what to do, how it will tell you. You have a lot of help. Okay.
Okay.
All right.
One
guys.
thing, Harun, I don't know, like if everyone is okay or not, but can you make it as white, the notebook, so that at least when we view from phone, it will be much easier to see? I don't know if everyone is comfortable.
Okay, yeah, sure. We'll do that. I'll change that next time. It should be there somewhere in settings. I'll do that. All right. Thank you so much. Appreciate you taking time today. So
you.
I will upload the recording and publish the notebook by evening today. Once I get that recording and processed. And we'll meet tomorrow. Okay. We'll
Right.
do
Thank
some.
you, Harun.
Thank you.
Well,
Thank you,
Thank you,
Harun.
Arun.
Thank
Thank
you.
you.
Bye.
Thank you.
All right, guys.
Thank you.
Thanks.
Thank you.
Thanks,
Thank you.
Harun.
Bye.
Thank you.